Cool. What's the definition of continuity at a point?
For all epsilon greater than 0, there exists a delta greater than 0, such that for all x in figure, if 0 is less than absolute value of x minus p is less than delta, then f of x minus f of p is less than epsilon.
And the absolute value version that you probably meant. So usually when writing the definition of continuity, you don't have that 0 is less than. It doesn't actually change the definition. What you said was equivalent. But since continuity actually cares what happens when x is equal to p, the point of the 0 is less than is to exclude what happens when x is equal to p. Of course, when x is equal to p, when with the zeros, if this is equal to 0, then x is p. So these two things are equal, so that difference is also less than epsilon because it's 0. Cool. So there is what continuity means. I want to assume f is not continuous. So let's negate the definition of continuity and see what it is that we get to assume. So if you negate this, what do you get? And as is traditional, that line is not as long as it should be. Yeah, right. So if it is not the case that something is true for every epsilon, that must mean there exists an epsilon that's a counterexample. So a universal quantifier becomes existential. There exists a delta. So if it is not the case that there exists a delta, that must mean that for absolutely every delta, the stuff after it fails. Not for every x in U means that there exists an x that is a counterexample. The negation of an if-then means that it must be the case that the assumption is true and the conclusion fails. So, yeah, that is, in fact, what we just straight up get to assume. And now let's remember the goal. We want to find a sequence that detects the failure of continuity. So I need to cook up a sequence. And I have a single choice of epsilon that I don't get to choose. Either God or the devil handed it to you, depending on what you think not continuity is. If it's good, then I guess it's from God. If it's bad, then it's from the devil. That's dumb. I know something is true for absolutely every choice of delta, and I want to come up with a sequence. So let's use a sequence worth of deltas to get something. What's your favorite sequence of positive numbers that converges to 0? 1 over n. Oh, it's written. So I have a single choice of epsilon, and I know that no matter what delta I pick, there exists a corresponding choice of x. So there exists an x that I'll call x sub n, right? X depends on the delta depends on n, so x sub n is a fine thing to call it, such that this happens. And right now, that epsilon is just like a fixed constant. So let's try to convince ourselves that this will probably do the job. Have we constructed a sequence of elements of the domain? Yep, hope so. Using this line, is it clear that that sequence of inputs converges to the target value p? Yep, because delta n goes to 0. Is it clear that f of xn does not converge to f of p because of this? Oh, cool. So in some sense, like, if this were like a paper, then like the conclusion would just be this is the sequence that does the job we want. Should we go through and check the details? Their demand? Very good. Let us do. So, since xn is u for every n, xn is a sequence of elements of u. We have constructed that something that exists, at least something that satisfies the thing right after that there exists. Xn minus p is less than delta n, which is equal to 1 over n. And we certainly have this delta n equal to 1 over n converging to 0. So I guess like I'm suppressing some details. I'm just saying here that now it's obvious that xn minus p goes to 0. Is that clear? I guess if we wanted to prove that, we could use like the squeeze theorem. Xn minus p is something between minus delta n and plus delta n, both of those goes to 0. So squeeze theorem says the thing in the middle does. We could do like an honest to God delta n. Delta already has a job. Small number, comma, n approved to do it. Xn minus p goes to 0, so xn converges to p. We feel pretty good? All right. Now, we need to show what remains. We need to show what do we know right now? We know that the absolute value of f of xn minus f of p is always greater than or equal to this fixed positive number epsilon. Oh, so what do we have? We know right now that there exists a single positive number epsilon, which satisfies that no matter how big little n is, the distance between f of xn minus f of p is bigger than or equal to epsilon. Well, that sounds an awful lot like it just immediately says that the sequence does not converge to f of p. I don't know. Does that feel like enough detail? People want to see the more detailed proof of that line? Yeah, you could come up now, you could say, well, let's suppose for the sake of contradiction that it did converge and go from there if you wanted to. Oh, so now I guess we're ready for the summary. Have we produced a sequence of elements of the set in U? Yep. Do we have xn converging to p? And we have f of xn does not converge to f of x. So, what have we shown? We've shown if f is not continuous at some fixed value p, then there exists a sequence xn of elements of u such that xn converges to p and f of xn does not converge to f of p. So what I'm going to do in these remaining couple steps is just backtrack through the logic that we used to set it up to make sure that we've actually proven what we want to prove. So we assumed f is not continuous. So way up at the top, not f is continuous. Is this statement right here exactly the negation of the thing at the top and the not? So on the next slide, I'm just going to point out that, oh, look, we've proven this. Or equivalently, we have proven if it is the case that not f is continuous at p, then it is not the case that for every sequence xn of elements of U, if xn converges to p, then f of xn converges to f of p. And you know what I'm about to write next, right? Like, I'm just wrapping up the proof. The actual analysis is already done. Now I'm just doing a little bit of logic. By the principle of contraposition, this implication is the same as that same implication with the arrow reversed and the knots erased. Should I use it with the arrow pointing forward, or should I use a right pointing arrow? People would rather just have the arrow reversed. It doesn't matter. It doesn't matter. You know what I'm going to write? I'm going to put this here and that there. And here's what's important about this result. This result says that if you know something about continuity, then you know something about sequences. If you want to prove something about continuity, you could prove something about sequences. And the definition of continuity is super close to the definition of the limit, right? You think you could do like a super similar proof and prove the corresponding claim for limits of functions? Challenge problem announcement, do that. It's probably about the same amount of walk. Maybe the 0 is less than, throws like a minor wrench in some gears. Not a big one, though. You just have to deal with the 0 is less than. Neato. So, let's prove the next thing on the list, which is the extreme value theorem. And the way that I think I want to prove the extreme value theorem, which will just flow most naturally, will involve exactly this notion of sequential continuity. So, let's do it. Let's start by stating the extreme value theorem. So there are two results that you maybe remember from like, well, let's just try to remember the extreme value theorem. If I say here's a function defined on some closed bounded interval and ask you how to find the maximum value this function takes, like what's the procedure you follow? Yeah. Let's maybe even be super explicit. X cubed plus x squared plus x plus 1. Suppose I asked you to maximize that over the interval from -5 to 5. Yeah.
Since it's like strictly increasing, the greatest value would be at 5.
Shit, it is strictly increasing. Change some of those plus signs to minus signs.
No comment.
Wait, shut it, right? Like, the game is you take the derivative, set it equal to 0, that finds critical points. You evaluate at those and you evaluate at the endpoints. One of those achieves the maximum value. There's one, like, in this class we don't talk about the derivative. That happens in analysis too. Not because it's hard, in fact, because it's easy. You can, like, figure out the derivative stuff on your own, really. Here's the important thing that is left out of that detail. A priori, you don't know for a fact that the maximum value exists. There doesn't have to be an input that produces the max. You need to, like, have a reason to believe there is. And that's what we're going to prove today. The maximum principle says that if I equal to AB is a closed bounded interval, and f is a continuous function defined on that closed bounded interval, then there is a single input C in I such that for all x in I, f of C is bigger than or equal to f of x. That seem like a maximum? There's a single input that produces an output that's at least as big as every other output. And the same thing happens with the minimum principle. If you have a continuous function on a closed bounded interval, there's a single input that produces the minimum value. There might be lots of inputs that produce the minimum. That's okay. So I'm going to take this and instead turn it into like a single theorem, and that's the theorem I'll prove. The extreme value theorem. Let I equal to A be a closed bounded interval, and F be a continuous function on that closed bounded interval. Then the supremum of the image of that function and the infimum of the image of that function are both in that in F of that closed bounded interval. So the maximum and minimum principle are like less technical sounding. The extreme value theorem stated there is slightly more technical sounding. Let's just check that it implies the two results above. So let's try to do that. Say a few words about why the maximum principle follow from the statement of the extreme value theorem. And let's start with this. So maybe we'll start with this. The assumptions of the extreme value theorem, are they the same as the assumptions for the maximum and minimum principle? Okay, that's good. So there's no issue with the assumptions not lining up correctly. So by the extreme value theorem, I'm going to focus on the supremum. The supremum of F of I is in F of I. That's just like what the EVT says. Well, what can you do with that? What does it mean to be in F of I?
Plug into the function to end up with the output being something from I that you can plug in. Yeah.
Sorry, you're saying everything reasonably. I'm just trying to translate it to like more technical words. So there should be something in the domain which does what? Well, I guess you said what, so that when you plug it in, you get the supremum? And you know what, let's switch back to pink because that bit of blue was just unraveling that. The maximum principle says that there is some C in I that does some stuff. Let's check that this C does that stuff. So let's let X be in I, and my eventual goal is F of C is bigger than or equal to F of X. There's the goal. Let's try to get there. Why should that happen? See, that F of C is the supremum of something. Is F of X in that something? Oh, if I just like put those into ones, does that give me the inequality I want? Oh, awesome. Then like, sometimes in math something is easier done than said. And like, what done, and now we just have to say it. Let X in I. So I think what's important is that F of X is in that set. Then F of X is in F of I. F of C equals the supremum of F of I is an upper bound on F of I. So f of c bigger than or equal to f of x. That seems sensible? So there are like two different avenues to approve, and I kind of decided which one I want to do already. Two avenues up towards this proof in this particular set of notes. And here they are, and you'll decide which one you would like to see. So here's one avenue. There's one avenue that is going to pass through a bunch of sequences. We're going to construct a sequence of inputs that like sees the supremum. We'll take the limit of that sequence of inputs. I guess we'll need to know that the limit exists and is in the domain, and then continuity will do the job. So there's one path. The other path will appeal to compactness. So we'll like get an open cover that's trying to see the supremum or something. We'll try to use that open cover to find that the supremum is in the set. So maybe we'll see what people feel more comfortable with. Sequence of inputs. Something about compactness. All right. Sequence of inputs has it at a total of 3 to 0 with 5 abstentions. So, as with many elections, this vote was decided by the people who did not vote. That's fine to do it here, but like, maybe I'll pontificate a little bit on politics. If you haven't registered to vote and are like able to register to vote, you probably should. You can do it at the polling place, but like, you can also register and get them to send the polls to you. Okay, I'll stop. Let's try to build a sequence that will detect the extreme value theorem. So, let's just recall the extreme value theorem. Let I be A be equal to a closed bounded interval. Then supremum of f of I and infimum of f of I are both in f of I. Step 1, let's check that the suprema even exist. What types of sets have suprema? What are the two things it needs to be to have supremum? Bounded and non-empty. It's obviously non-empty, right? F of A is in the set. So we just need to prove that the sucker is bounded. What kinds of sets have suprema / infima? Non-empty, bounded sets. Spelling is so very difficult. So we need to show that this set is non-empty and bounded. It's obviously non-empty. F of A is in the set. Let's write that. F of A is in F of I. So F of I is not equal to the empty set. So let's try to prove that if you have a continuous function defined on a bounded interval, that the result is bounded. And so like, that seems hard to do directly. If I show a thing is bounded, I need to come up with a candidate upper bound. So that seems too hard. Instead, let's proceed by contradiction. We will come up with a sequence of inputs for which something bad happens. That seem sensible? Let's try it. So, let's let A be, let's let I be a closed bounded interval and F be a continuous function on this closed bounded interval. If we're going to prove this lemma by contradiction, what do you think I want to assume? F of I is not bounded. And maybe I'll even be more specific. If it's not bounded below, do you think I can come up with something similar to whatever it is I'm going to do? So I think that maybe I'll include this sentence. We will only prove that it's bounded above. All right, so this sucker is not bounded above. I want to construct a sequence that sees the failure of bounded aboveness. So I think to do that, I'm going to pick my favorite sequence that goes to infinity. That sequence. That's not an upper bound. So n itself is not an upper bound on the set f of I. Sorry, I said the thing that was going to go into blank. That can't be an upper bound because it has no upper bounds. Ooh, since that is not an upper bound, there must be something in the set that does something. What's the something that it does? If n is not an upper bound on f of I, then there's something in the set with. Which is just bigger than that non-upper bound. If a thing is not an upper bound, there's something in the set, what's bigger than it? And you know what, from here maybe we'll draw a picture. And this will also indicate why I'm using yn. So here is this closed bounded interval. Here's this continuous function. I'm drawing it like it's not bounded above. There's obviously like a problem in this picture. There's a vortical asymptote or something. I need to like prove that there's a vortical asymptote or something. So right now, here is n. There's yn, there's an output that's bigger than n. And now let's play with this. That's an output of this function. It's something in f of I. Since yn is in f of I, what does that mean? Yeah.
That n has to be in a for I. Or, sorry.
I don't think n does. There has to be some input that goes to it?
Yn,
Yeah. So yn is in f of I, so there must be some xn that goes to it? Cool. Like this graph isn't part of the proof, but it's maybe helpful to illustrate the proof. So let's use that. Oh, God damn it. Okay, going somewhat out of order. Since yn is in f of I, the definition of the image of a function implies that there is some xn in I, so that f of xn is equal to yn. Yep. Nothing fancy there yet. Let's fill in the gap that What can you tell me about? Since I know that for absolutely every n, yn is bigger than n. What can you tell me about the limit of yn? Sure, that's true. Maybe I'll say bigger than or equal to, because sometimes limits can turn strict inequalities to loose inequalities. As n goes to infinity, though, where does n go? Infinity. So the limit of yn is at least as big as infinity. So what can you tell me about the limit of yn? But we have a name for that. So just hold on to that. That means the sequence yn diverges to infinity. Let's muck around with the sequence xn that we've got, though. That sequence xn is always between a and b. So what word would you use to describe this sequence xn? Bounded. Do we know anything about bounded sequences? there's like a special named theorem that I've had a previous student who refused to call by the right name and instead called it bozo wild sauce. This theorem says that any bounded sequence has a convergent subsequence. So I can throw out some of the choices of these subscripts and get a new sequence that converges. So maybe you're starting to see something. The sequence of xn's after you throw out some inputs converges. So that's like an x sub n sub k. Y sub n sub k, what will that do? Well, if y sub n goes to infinity, then probably the subsequences do too. In fact, they'll go to infinity faster. So I have a sequence of inputs that converge. Sequence of outputs diverge to infinity. The sequence of inputs, is it going to converge to like a valid input for the function? I think so. It'll be somewhere between A and B. So let's draw that. We'll get close to some input P. Oh, but notice the corresponding output values will shoot off to infinity. Limit of f of x sub n sub k cannot be equal to f of p. Oh, did we like prove that that can't happen if a function's continuous? Cool, I think there's a contradiction. Let's put it down in words. Since xn is in AB, we get an inequality. By Bolzano-Weierstrass, you told me what happens. This thing has this is a bounded sequence. Bolzano-Weierstrass says that this thing has a convergent subsequence x sub n sub k. So far, so good. In like the rambling I did, what value this x sub n sub k converges to matters. In that I want it to converge to a place where I know the function is continuous. So let's try to do that. I still know that a is less than or equal to x sub n sub k is less than or equal to b. Can I take the limit of that inequality? Yeah, limits respect inequalities. So if x is the limit of this sequence, I know that this thing is in the closed interval from a to b. Now I'm going to use the assumption this function is definitely continuous at this value x, because it's continuous everywhere. But like now maybe we're getting something bad happening. Since x is in I conclude that f is continuous at x by the theorem that we just finished proving. What can you tell me about the limit as k goes to infinity of f of x sub n sub k? It doesn't equal x.
What equals that? That was that.
There we go. Theorem 7.2.2 says that a function is continuous at a point if and only if for every sequence of elements that converges to the point, the limit of that sequence of elements is f of that limiting value. This sequence x sub n sub k converges to x. The function is continuous at x, so you get this conclusion. Feel good so far? We have half of our contradiction. The contradiction is going to be about f of x sub n sub k. Right now, I know f of x sub n sub k converges. On the other hand, yn is equal to f of xn. So f of x sub n sub k is a subsequence of y sub n. I know that y sub n diverges to infinity. If you take a subsequence of a sequence that diverges to infinity, what can you say about that subsequence? Also diverges to infinity. Oh wait, is that a contradiction? Yeah, what's the contradiction?
The limit is k approaches infinity of f, x and k is not equal to itself.
Yeah, right. Yeah, so maybe there's, the limit is a number, but it's also infinite. Can't be both. Oh, but that's not what goes in that blank. This is a contradiction. So it must be that f of I is bounded above. Do you think you could adapt this proof to get bounded below? Yeah, I think like the false difference would be changing your choice of y sub n. To get bounded below, I think you'd need something different. You'd instead want to take a sequence that goes to minus infinity. What's your favorite sequence that goes to minus infinity?
F of x equals negative x.
Yeah, except I want a sequence, so negative n. Oh. So I think I'd want negative n, and I think I'd want that inequality. Oh, cool. After you do that, do you think you just push through the exact same argument? Yeah. Some extra negative signs and maybe some inequalities would be switched. Groovy. All right. So far we have that the f of the interval from a to b is bounded above and bounded below. So the supremum and infimum both exist. Now we need to show that you can actually hit them. And the proof of that is going to feel very similar to this. I thought I was going to use sequential continuity, so let's use sequential continuity. So, maybe I'll draw a picture of it. Oh, I've got like 10 minutes, right? Yeah. Also, on the recording, there might just be like an excellent picture of my chin hair that showed up right there. Right before it goes blank. So, you have some continuous function on a closed bounded interval. We know it's bounded above. The picture I drew sure looks like it had, like the supremum is attained by an actual honest to God. But like, what if it won't? I'll draw a little sock over there. Can you always find like a sequence of things that gets close to the supremum? Yeah, I think like take the formula, the idea of the supremum that has like an epsilon in it, and take that epsilon to be 1 over k. So if there's the supremum, then go down here to the supremum minus epsilon. You can definitely find an output value that's in between the supremum and the supremum minus epsilon. That's an output value. Does it correspond to an input value? I think I want that to be y sub n. That corresponds to some x sub n. Is that sequence obviously bounded? Yep, it's always between a and b. So it's got a convergent subsequence. Jesus. They'll be constant. And there is a stairwell there. Jesus. Okay. So the sequence x sub n is bounded. Also, if I stress it has a convergent subsequence. Just based on looking at that picture, what does it look? What can you tell me about? Well, it has a convergent subsequence. That convergent subsequence has a limit. what do you think the limit of the outputs has to be? Equal to the supremum? Oh, but that means f of the limit should be the limit of the f's. The limit of the f's converges to, is the supremum. So f of the limit is also the supremum. Oh, hey, there's the input that goes to the supremum. So, like we have the proof now, it's just like trotting back from nonsense to math. Cool. All right, so let's do it. Let's let the setup. By the lemma, we have that f of I is bounded. It is obviously non-empty. We just proved that it's bounded. By the completeness of the real line, nope, that's too much, exists. As is my habit, I am basically going to forget about the fact that infimum is a thing, and I'll only prove stuff for supremum. We need to prove that sup of f of I and inf of f of I are each in f of I. We'll only prove it for the supremum. For convenience, let's call that supremum S. And we've already verbally sketched the proof. So we just need to go through those motions. So let's let S be the supremum of f of I. Consider any n in the natural numbers. S minus 1 over n. Could that be an upper bound? No, why not? Less than the supremum. Supremum is the least upper bound. Nope. So, that sucker is not an upper bound. Well, there's an input that sees that that's not an upper bound. There's some y in f of I which satisfies what? Yeah, in fact, I think strictly less than, right? Failure to be an upper bound means there must be something in the set that's strictly bigger than. I can see why you said less than or equal to, because I think the next line has less than or equal to, right? So I think there's what you technically get. You get something slightly stronger than what I wrote. So yn is in between s minus 1 over n and s. What can you tell me about the limit of y sub n? Between the limits of those two things? Are those two limits the same? Yeah. And in fact, if they weren't the same, what you said wouldn't quite be correct. You wouldn't know that the limit exists. Yn converges to S. It's a cursive S, but I shouldn't change script. So Yn converges to S. All right, so I have a sequence of outputs that converges to S. I can change from outputs to inputs. The definition of the image of a function says that there's something in the domain so that f of xn is equal to yn. Keeping an eye on time, I got 5 minutes. And I think we know what I'm going to do, right? Because we've said what I'm going to do. This sequence xn, is it obviously bounded? It's between A and B. This is bounded. Bolzano-Weierstrass says it has a convergent subsequence. All right. But remember, oh, yeah. Right, there's an order you could do these things in. I think I should follow the order that's written. the limit is in the domain of the function. That's what that line says. So maybe I'll even write this sentence. F, well, it's right here. F is continuous on I. So F is continuous on all of I, so F is continuous at X. So that means the limit as k goes to infinity of F of X sub n sub k, what should that be the same as? F of X. That's good. Hold on to this. This will be important. Let's go back to thinking about the y sub n's. So let's remember what we have right now, that y sub n converges to the supremum. So if y sub n converges to the supremum, then notice f of x sub n sub k is a subsequence of y sub n. If y sub n goes to the supremum, then where do its subsequences go? Also the supremum. So maybe you notice based on what I just crossed out, there was an awful lot of copy-paste, and maybe that feels an awful lot like it, because this is almost exactly the same proof as we just gave, which converges to S. Thus, the limit of this is equal to S. This is not a contradiction, but let's think about what we wanted to show. We wanted to show that the supremum of f of I is in f of I. So we wanted an input which this function sends to the supremum. Do we have a name for that input right now? What is its name? Well, let's just summarize. So right now we have the limit. We have f of x is equal to the limit f of x sub n sub k by star. On the other hand, what else is the limit of f of x sub n sub k equal to? S. Which was the supremum of f of I. Does that line say that there is an input which the function sends to the supremum? Oh, cool. That's exactly what we wanted to prove. And maybe I'll ask like the same question as I did about the previous proof. Think you could adapt this a little bit to get the infimum? So here is how I am going to close today. You'll notice that the next subsection is another proof of the exact same theorem. In fact, it's a proof of a slightly better theorem. In the language of compactness, here's an important topological result. If you have a compact set and hit it with a continuous function, the image is still compact. Since compact sets contain their suprema, that proves the extreme value theorem. In fact, it proves something way better. There are lots of compact sets that aren't closed bounded intervals. The extreme value theorem holds over any of those things. Complete that section, there's a challenge problem. I would not call it one of the easier challenge problems, but it's not one of the harder ones either. A note on the homework is there's like an if-then in the homework depending on which path we took through the notes. There's the actual homework. If you complete the compactness-based proof, then that will unlock for you a bonus homework that I'll count as having the same weight as a homework, but being bonus. So if you do that and get 100% on it, it's as if you have 200% on one homework assignment. I think some of you need that less than others, but I don't think anyone has a super low homework score. If you're unhappy with it, there will be some bonus homeworky things coming up. Nice. So I'm over time, so you should be packing. A thing that I'll try to get onto Canvas soon is, since sufficiently many people still need to complete the challenge problem, I'm going to compose a list of what I feel are the most attainable challenge problems, because they're certainly not of a uniform difficulty. So if you just need to get one done, a list will appear in Canvas of some that you might consider thinking about soon. Cool. And as of today, there are 3 meetings left before Thanksgiving. Yeah.
This class last week, but for the homework that's due tonight, third question, I can't remember what the number comes to, but I think is it just basically the exact same as the first question?